All right, we're going to reduce this system to reduced row echelon form. Along the way, I'm going to record the elementary row operations that correspond to that, and then that'll produce a sequence of matrices that will allow us to then multiply out and solve our system, or write it in reduced row function. Okay. All right. Well, with that, um, the first thing to note is that I want to reduce the elements below the leading one, the pivot here, to 0. And so to do that, I'm going to first take -1 times row 1 and add it to row 2. So I'm going to take the opposite of this and add it to this row. Okay. So 2, 1, -1, 1. And if I do that, that's going to be -2 added to 2 makes that a 0. It's a -2 or -1 added to 1 makes that a 0. Negative and a negative makes that a +1. Adding it to -1 makes it a -1. And making that a -1, adding it to a -2 makes that a -3. Okay. So this is going to be my first elementary matrix. And then I'm also going to eliminate this row. I'm going to eliminate this leading one here, or eliminate this to a 0 here. So I'm going to take a -2 times row 1 and add it to row 3. And so 2 times the negative row 1 and adding it to row 3. If I do that, I'm going to have -2 times 2 is a -4, added to that is 0. The -2 to a +1 is a -2, adding it to 3 makes that a 1. And a negative times a negative makes that a +2, adding 2 to 2 makes that a +4. And a -2 to a +1 makes it -2, adding it to 16 makes that a total of 14. And so here is my E2. Okay. That's equal to that. So let's go ahead and write those two as matrices before we get too far down the line. So E1 is equal to negative row. And so remember, I'm transforming the identity matrix in each of these. So in each case, even though our system matrix is changing, we're always going to be referring back to the identity matrix. So a negative row 1 and adding it to row 2 would make this a -1, 1, 0, 0, 0, 1. Okay, so that's E1. And then E2 is 2 times row 1 and adding it to row 3. So the first two rows don't change. 2 times row 1, adding it to row 3 would give me that as my second elementary matrix. Okay. So now you notice that I need a pivot or a leading one for the second row. And so I'm going to interchange these two rows. So that'll actually be my E3. It's changing row 2 with exchanging it with row 3. Okay, so it's going to be 2, 1, -1, 1, 0, 1, 4, 14, 0, 0, -1, -3. Okay, so our E3, this is going to be exchanging these two. We're going to have 0, 1, 0, 0, 0, 0, 1, 0, 1, 0. Exchanging those two rows. Okay. All right, we're going to expand this a little bit further. Okay, so upper triangular already, and that's a really good start. So now to eliminate the one up here, all I'm going to do is take opposite of row 2 and add it to row 1. Okay, and so 0, 0, -1, -3. I don't know why I do that, but there we go. 0, 1, 4, and 14. Okay, so I'm going to take opposite of row 2. So this is going to stay the same. This is -1 now. Add to that, that's 0. This is opposite is -4. Adding it to a -1 makes this a -5. Okay, and then opposite of that is -14. Adding -14 to a +1 makes this a -13. Okay. All right, and so this, of course, is our E4. So E4 what is it? It means opposite of row 1, or row 2, and adding it to row 1. So the negative 1, and that would be it. So the opposite of row 2 and adding it to row 1. So there we go. All right. Okay. Let's see what else we need to do. We need to eliminate these two terms. So it looks like if I do negative 5 times row 3 and add it to row 1, that will be my E5 already. Huh. Okay, so row 3 is the only one that's not going to be changing here. Drawing that line kind of helps me keep things balanced. Okay, so here we have negative 5 times that's 0, so this is going to stay 0. That's 0, so that's going to stay 1. This is a negative times a negative, so it's going to be a positive 5. Adding it to, oh, yeah, this is going to stay the same here too. Adding this to, so it's going to be a negative 5 times the negative 1 is a positive 5. Adding it to that negative 5 makes that 0. The negative and the negative makes it a positive 15. Positive 15 plus 13, negative 13, right? Gives us like a 2. Okay. So our E5 then, of course, is going to be 1, 0, negative 5, 0, 1, 0, 0, 0, 1. Okay, so that's E5. And then to get rid of this 4 here, I'm going to take my E6, going to be negative 4 times row. Actually, no, it's going to be positive row 1, row 3, and adding it to row 2. Okay, so that'll be the same. That'll be the same. This will be a negative 4, adding it to that, will make it 0. This would be 4 is negative 12. Negative 12 to 14 will make that a positive 2. Okay, and then our E6 is getting equal. Let's see, we're going to multiply row 3 by 4 and add it to row 2. So 0, 1, 4, 0, 0, 1. Okay. All right. It looks like we just simply need to multiply row 1 by a half. It's going to be E7. And E8 is going to be opposite of row 3. Okay, so E7 is going to be 1 half 0, 0, 0, 1, 0, 0, 0, 1. And E8 is going to equal 1, 0, 0, 0, 0, negative 1, 0, 1, 0. Okay, and so our final result is 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 3. And that's the same result that we saw in our previous example, just with a different format. And so the product of each of these elementary matrices, so they result from operations, individual row operations on the identity matrix, produces then in a sequence a product. And so if we kind of think about what that might look like, so here it is written out. So if we write out each of the individual elements, E3, E8 through E1 as a product acting on A, the resulting matrix we get is the identity matrix with some augmented column, whatever that last column is, if it's not an n by, if it's not a, so if this was in a square matrix, then it'll be like ours, it's not a square matrix. And so we'll check to make sure that this is in fact what we get. We're expecting it to look like what we ended up here. And in our previous example, this was x1 or x2, x3, or x, y, and z. And these were the solutions, and this was the answer vector, but it doesn't have to be. It can just be an n by n matrix. So we should see that that's the case. So let's go ahead and transfer over to GeoGebra and see if the results correspond to what we were expecting to see. All right, now that we have GeoGebra up, I'm going to go ahead and enter in each of these matrices, and then once we do that, we'll plug in the product and see what we get out. I'm not going to talk in this time. I'm going to fast forward this so you don't have to sit there and watch me enter all of them in real time, but rather as in a fast forward state. So here we go. Now we're going to go ahead and multiply these out. E8 times E, and you can't miss the fun, E7 times E6. So you should be looking right here and watching the transform as each of these products get implemented in. And it's cool to see how it's evolving. 2, E1, okay. And so when I put in note A, what we should expect is something exactly like we did. And so we did. If we look here, we have the product of E8 through E1. So these are actually elementary matrices. And we have a diagonal of, oh, that is interesting. So there's where was E8? There's an extra negative there. Okay. It wasn't acting exactly right. And what had happened was up here at E7, I had an extra negative at this component just to show you. Plug in a -1 there. You can see how it switches back to what we had a -1 and a -3. So I had a extra negative in my E7 term here. Turning that back to what it should be, see that in fact our product of elementary matrices gives us exactly as we expected. Our identity matrix, a 3x3 identity matrix, and our column vector answers from our previous problem. So this is a really powerful way of getting at a solution or solving a system or finding the inverse actually is one of the major reasons why we utilize this process. It produces more complicated systems. It reduces it down to a product of simple invertible matrices, which is really helpful for several applications. So anyways, this is elementary matrices, and I hope this video was helpful, and I look forward to working with you in the next one.